Hey everyone, I hope you are excited for today's lesson on factored form. For this lesson, you should have a pencil in your hand, your notes printed out, and your brain ready to work. Let's get started. So, throughout this unit, we've talked about a few different forms, okay? Let's kind of take a look at some of the forms we talked about. You started off our unit by talking about standard form. Each of the forms of quadratic functions have different qualities. In a standard form, we know that we can pull out the vertex by first finding the axis of symmetry by calculating x equals negative b over 2a, then by plugging into the function to find my y value. Simply by plugging in x for 0, we can also find my y-intercept. So standard form gets us a lot of information pulled out. The next topic we talked about was vertex form. From vertex form, surprise, we were able to pull out the vertex very quickly. Today's lesson is focusing on factored form, all right? And we know if something is factored, we are writing it as a product of its factors. So let's kind of get started with our first example and our first definition, all right? When we talk about factored form, factored or intercept form, you might hear either of those, is y equals a times the quantity x minus p times the quantity x minus q. Let's talk about some of the characteristics of the graph. In factored form or intercept form, the x-intercepts are p and q, which we can simply pull straight out of this equation. Please note that p and q are negative form in the equation, so when you are pulling it out, make sure to take the opposite of each of those, all right? When we talk about the axis of symmetry, well, if p and q are the x-intercepts, the axis of symmetry must be halfway between p comma 0 and q minus 0, q comma 0, all right? Which kind of makes sense, right? I'm going to quickly draw a quadratic function here. If this is my quadrant and my parabola is located here, and these are my x-intercepts, these are my p and my q values, all right? Now, if we're looking for the axis of symmetry, we know our axis of symmetry must be halfway between those 2 points. So when we talk about how do we calculate the axis of symmetry, unlike standard form where we do negative b over 2a, we can actually look at p and q and we know the axis of symmetry is the halfway point between those two x-intercepts. So to calculate that, I do p plus q all over 2, or divided by 2. We find the halfway point between p and q. All right. A also still plays a really important part in factored or intercept form. We know if A is greater than 0, the graph opens up. If A is less than 0, the graph opens down. A also tells me if the quadratic function is vertically stretched or vertically compressed. All right, so those things still come into play when we're dealing with factored and intercept form. Let's take a look at our first example. In number 1, we have y equals negative 2 times the quantity x minus 1 times the quantity x minus 5. So I'm going to first pull out my x-intercepts, all right? I know we have a p value and a q value. I take the opposite of that. So my x-intercepts must be 1, 0, and 5, 0. It is important that we have our x-intercepts written properly with those parentheses and that comma in between. From here, I'm going to try to find my vertex. Well, I know I can find my axis of symmetry by first calculating the halfway point between p and q. So I'm going to write x equals p plus q all divided by 2. Well, if p is 1, q is 5, divided by 2, my x will be 3. That's going to be my axis of symmetry, so I'm going to fill that in immediately. X equals 3. From here, I'm going to plug in that x value back into my original function to now calculate my y value to give me that vertex. So if my x is 3, what's my y? Well, let's calculate that. We have y equals negative 2. I'm going to zoom in here just so we can kind of write that a little bit better. All right, negative 2 times the quantity 3 minus 1 times the quantity 3 minus 5. All right, negative 2 times 3 minus 1 is 2, 3 minus 5 is negative 2. We get y equals positive 8. So I know my vertex, now if I zoom back out, my vertex is 3, 8. Now from here I can immediately plot my vertex on the graph if you want. I like to start by filling in my table. So I'm going to put that as my middle point. From here, I want to actually start determining different x values that I can plug into my function to fill out my table. Now I want to pick some values at above and below. Now I'm going to first start off by going below 3, and I'm going to start by 1, because I notice if I plug in 1 into my original function, I get 0, and that's going to make it really easy to calculate. All right, you have some option here in this space on the bottom. If you want to create a whole table and actually plug in your different x and y values, that's totally fine. You don't need to though. So if I plug in 1, I'm going to show that work here. Y equals -2, 1 minus 1, times the quantity 1 minus 5. I see that cancels out to 0. So my whole answer is y equals 0. All right, now if I take a look and I go, all right, what's one more towards the left of that? Well, let's do 0. If x is 0, and I like to use 0 because that's a really easy number to kind of plug in, right? Y equals -2, 0 minus 1 times the quantity 0 minus 5. We get -2 times -1 times -5. That gives me -10. All right. If I were to kind of create my symmetry points, then I know 2 away from 3 was 1, but in the other direction, 2 away from 3 would be 5. When I plug that in back into my original function, I get 0. All right, and then I'm going to go the same distance away from 3 to 0. So 3 to another 3 over would be 6, and that should also give me -10. Once you have your table of values filled in, this is where you will want to start actually graphing. So I'm going to change this just a little bit, and we're going to graph. Let's actually graph in red. All right, so I'm going to zoom in so I get a better opportunity to actually graph this. All right, so I'm going to start by graphing 0, -10, 1, 0. Then I go to my vertex 3, 8. Everything should start flipping over now. We have 5, 0, and then we have 6, -10. I'm going to try my best to actually connect all these points to create that parabola, creating arrows at the end to show that reader that that function continues on. All right, once you've actually filled in the table of values and graphed it, now we can start filling in the rest of the features of this graph. Well, if I'm asked to find the domain, remember domain's all your x values, and in any quadratic function, the domain we scan from left to right, and it's always all real numbers. So I'm going to immediately write in all real numbers. Now my range, we look at the y value. So I start from the bottom and I work my way up. Now in this case, my range depends on my vertex, right? And since my vertex is at y equals 8, we know it's all values less than or equal to 8. So you can write it as y equals less than or equal to 8, or you can write it in set notation. So -infinity to 8 with the bracket inclusive. My vertex is a max. The direction of the opening is down. It's facing downwards. We already filled in my axis of symmetry. Now we have to compare the width of this quadratic function to our parent function y equals x squared. And that's where we focus on the a. Since my a is -2, the absolute value of a is 2, right? And that tells me that my graph in this case is narrower than my parent function. All right, so we've done our first example. What I would like you to do right now is take a look at number 2 and 3 and try these out on your own. In number 2, your axis of symmetry does come out to be a fraction, so don't get alarmed by that, but try your best to actually apply what we did in number 1 for number 2 and number 3. So at this point, please pause the video, and then when you're ready, come back and check your answers to 2 and 3. All right, so hopefully you finished 2 and 3. All right, and we're going to go over the solutions right here. The first thing I did was to find my axis of symmetry. So I first found the first thing I did was find my x-intercepts. I looked at my p and my q values, and I found the opposites of those, right? So we have my x-intercepts 3, 0, and -2, 0. Make sure you have those points as it is written on my notes page. From here, we found our axis of symmetry, and we found that by plugging in p plus q divided by 2. We found that halfway point between those two x-intercepts. And we got x equals 1/2. Once we found our axis of symmetry, we plugged it in to find the vertex. My vertex should have been -1/2, comma, -3 1/8. All right, if you had it as a decimal, that's okay. We're going to keep going though. From here, we plugged in our vertex onto our table of values. And you're going to notice I have some work here on the bottom showing how I plugged in some values above and below that point. I filled in all these values on my table by evaluating my x value back into my original function to get my y values. From there, I plotted my points. And then, after I plotted my points, I started examining all my key features. We know my domain is all real numbers. My range in set notations is -3 and 1/8 inclusive to all the way to infinity. My vertex was a min. The direction of the opening was upward. And this, compared to the graph of my parent function, is wider because my a value was 1/2. Okay, so this was a vertical compression. All right, let's take a look at number 3. In number 3, we started off once again with my x-intercepts, -3, 0, 3, 0. We plugged it in to get my y value, we plugged it in to get the halfway point, which is my axis of symmetry, x equals 0. We plugged in to get your vertex, 0, -9. From here, we started to fill out the table of values, and you're going to notice here on the bottom, this is what I meant by if it helps you to actually create a bigger table and actually plug in the work there so you know you're evaluating correctly, that's totally fine, but that's optional. So we filled in the values above and below my vertex, we graphed it, and then we looked at its key features. We saw that the domain's all real numbers. My range is y is greater than or equal to -9. Notice how I wrote this in set notation. My vertex was a min, the direction of the opening's up, and since my a value is 1, this is the same width as my parent function. All right, now that we've done some work with practicing how to graph and look at key characteristics in factored form, let's start talking about some application problems now. Number 4 and number 5 are really wonderful application problems that you're going to see a lot as we move through our quadratic functions unit, and this will also continue when you guys are in Algebra 2. All right, so let's take a look and we're going to dissect this problem and talk about different strategies we can use to solve this. Let's say calculators are sold for $20 each to students. At this price, 300 students are willing to buy them. For every $5 increase, there are 30 fewer students willing to buy the calculator. So we're going to use this function r equals quantity 20 plus 5x times the quantity 300 minus 30x. All right, so I'm going to zoom in on this just a little bit. Let's first start with what those values represent. Well, we know r represents my revenue, all right? So we can say r equals revenue. And in this case, my x represents the number of my price increases. All right, how many times am I increasing the price? Now let's actually dissect this function. Well, I'm going to use two different colors here. We're going to start with orange. Calculators are sold for $20 each. All right, in this first binomial, we have 20 plus 5x. That $20 represents how much the calculators are sold, and the $5, 5x represents for every $5 increase in price. So if x represents the number of price increase, if I only increase it one time, it's going to be $25. If I increase it 2 times, it'll be $30, and so on, right? So that's what that first binomial represents. So this is going to represent my cost. And when we get, I'm labeling this right now because when we get to number 5, they're going to actually ask you to write the function. So kind of looking at some of these key features will help you. All right, let's look at the second binomial here. We have 300 minus 30x. I'm actually going to change this to green. Well, this 300 represents the 300 students that are willing to buy it at the first price of $20. But every time I increase the price, we're going to decrease the number of students that are willing to buy it, right? And think about that logically. If you start increasing the price of something, you have less people that are probably willing to buy it. So that 30 fewer students is represented by minus 30x, because for every time I increase the price, I'm going to subtract 30 students. So this binomial represents the number of students purchasing. Okay, let's get to our first example now. I'm going to switch over to blue. All right, in part A, it says how many price increases will produce the maximum revenue. So they're asking for two things that I'm going to pull out this information this question. How many price increases? So I'm going to solve for x, and they're asking for the maximum revenue. Whenever I see maximum revenue, I'm thinking the vertex. At what point is it going to hit that topmost point? All right. Since our original function, which I'm going to highlight in purple right now, is not in factored form, I'm going to put it, since it is in factored form, I'm going to put it in standard form first. Okay, so follow along with me as I do this. I'm going to take my original function, r equals 20 plus 5x times the quantity 300 minus 30x. All right, this is in factor form. I cannot actually pull out my vertex here. Unlike the other examples that we did above this, this isn't really in factored form because we have it's not as easy to pull out my vertex, that's what I mean, in this factored form, okay? So I'm gonna actually put it in standard form first, and the way we do that is really just by double distributing here. So go ahead and do that in your notes as I do this on my paper. When you double distribute and simplify it and writing in standard form, we get r equals negative 150x squared plus 900x plus 6,000. All right. Now that we actually have it in standard form, this is where we can go ahead and try to find my axis of symmetry. At what value of x, right, will I have my max, or will my vertex hit? So I find that in standard form by doing x equals negative b over 2a. I plug in my negative b, negative 900 over 2 times negative 50. Negative 900 over negative 300. So x equals 3. All right, I apologize for the little messy handwriting here. So 3 price increases will produce the max revenue. All right, so that's the example, that's the answer for example A. All right, let's move on. I'm going to change my colors here just so we can differentiate between the work. We're going to use a light blue now. So at what selling price will produce the maximum revenue? Well, this is where we can kind of use some logic, right? If x equals 3, that means that I'm increasing the price 3 times. So you have a few different ways. You can just calculate it mentally, or I can actually go back to this top part where I look at my original binomial, my first binomial, 20 plus 5x, because that represents the price, and I'm looking for the selling price. And I say if I'm increasing the price 3 times, well, 20 plus 5 times 3, so that gives me 20 plus 15, so it's $35, okay? So with 3 price increases, my selling price will be $35. Now, let's actually figure out what's the maximum revenue now. Well, if I know 3 price increases, well, let's plug that in now to figure out what's my actual revenue. So I look at my original function. You actually have 2 options here. Since x equals 3, I have 2 places I can plug it in. I can plug it into my original function, which is in factored form, or I can plug it in here where we put it in standard form. Either way, it should work. I usually like to plug it into my original function that's given in the problem, just in case I made any errors when writing in standard form. But it really doesn't matter. All right. Once I plug in x, I can solve for r to get my revenue. So r equals 20 plus 5 plus 3. 300 minus 3 times 3. All right, we get 20 plus 15 times 300 minus 9. Your revenue should be $7,350. All right. So now that we've gone through how to solve number 4, let's look at number 5. In number 5, they say when priced at $30 each, a toy has annual sales of 4,000 units. The manufacturer estimated that for every $1 increase in price, sales will decrease by 100 units. All right, so I can take a look, kind of like what we did in number 4. Number 4 had two binomials, and we broke it up by cost and number of students purchasing. So the first part asks us to actually write a function. I like to always start off with a let statement. So let's kind of do that. We're going to start by saying let R equal the total revenue. And let X equal the number of price increases. You might get some problems that have price decreases, which is nice. That this one's really similar to number 4, okay? But just keep in mind, these are both price increases. So let's first start off by writing my function R equals, all right? And we're gonna first start by talking about the number of units sold. So I'm gonna do that in green. When priced at $30 each, a toy has an annual sale of 4,000 units, but that sale will decrease by 100 units. So to first talk about the number of units sold, I'm going to do 4,000 minus 100x. Then I'm going to write my second binomial, which is going to represent the price or the cost. Well, it's originally $30 each, and it increases every $1 per increase in price. So I'm going to write 30 plus x. Okay, we now have our function. So what I want you to do is now use number 4 as kind of a guideline and solve B, C, and D. So pause the video, try to figure out the maximum revenue, how many price increases, what's the selling price, and what's the maximum revenue. Okay, hopefully you figured out number 5. We're going to go ahead and actually look through that. Okay, so over here in number 5, I have all my answers here. In part B, the first thing that we did was we wrote our function in standard form. So hopefully you got R equals negative 100x squared plus 1,000x plus 120,000. To figure out the maximum revenue and how many price increases, I need to solve for my axis of symmetry here. So I did x equals negative b over 2a. We got x equals 5, which means that there's 5 price increases. Since there's 5 price increases, I'm going to figure out, well, what's the cost? What's the selling price, right? If it's an original price at $30 and I increase it for $1 every price increase, well, we just plug it back into 30 plus x. So our selling price is $35. So at 5 price increases, the selling price is $35. The last question asks us for the maximum revenue. I take that x equals 5, I plug it back into my original function or into my standard form function, doesn't matter. Notice here I put it in my standard form function. Your maximum revenue should have been $122,500. All right, so after we've done that, part 2 of this video is going to be talking about how to convert between all 3 forms. If you need a break, go ahead and pause the video and break. But for right now, we're going to keep going, trucking through for part 2, okay? Part 2, we're going to take a look now, and we're going to start combining all of our knowledge between vertex, standard, and factored form. And this isn't too bad, okay? So in this first example here on your notes, you're going to notice that they're asking us to convert from factored form to standard form. So the example over here to the right, we have it in factored form. In order to write this in standard form, automatically, hopefully you have this urge to immediately simplify the expression to the right. And we know how to do that, right? We just did this in our past unit. In order to simplify this, we can FOIL, or in other words, double distribute. So y equals negative 2, we kind of double distribute. If you can get that second term in the middle to be simplified in your head, that's totally fine. Y equals negative 2 times the quantity x squared minus 3x minus 40. We get our final answer, y equals negative 2x squared plus 6x plus 80. And that's it in standard form. Please make sure you include the y equals, because remember, these are not expressions. These are functions and equations. So it is really important you show that relationship between the x and the y. So include that y in if you haven't done that. All right, so let's move on to the next one. In example 2, they're asking us to write it from vertex form, which you see on the right. This is in vertex form. And they want us to write it in standard form. Well, in this case, we kind of do the same thing. We want to simplify that expression to the right. And the way we do it is we multiply it. In this case, you're going to notice that we have a perfect square trinomial. And is that okay? Absolutely. This is why that whole unit we just did before really comes into play here with our quadratics unit. So I have f of x is equal to, I remember kind of some of the qualities of perfect square trinomials. So we have 4 times the quantity x squared minus 2x plus 1. If you need to actually write out x minus 1 times x minus 1, that's fine. Plus 9. All right, we're going to simplify that out. F of x is equal to 4x squared minus 8x plus 4. Oops, sorry about that. Plus 9. So my function written in standard form, f of x equals 4x squared minus 8x plus 13. Once again, please make sure you have that f of x because this is a function. All right, my last example with you, I'm giving it to you now in standard form. Ooh, and I want you to write it in factored form. Well, take a look back up here as a reference, what factored form kind of looks like. All right, well, how do we do this? We use what we did in our last unit, right? We have a trinomial here, and I'm asking you guys to factor it. So I take a look at this since my leading coefficient is prime. I personally prefer to use guess and check. If you'd rather factor by grouping, that's totally fine. Get that practice either way. For the sake of this video, I'm going to use guess and check though. So I'm going to set up my two binomials. I know since it's 2x squared, one of my terms has to be 2x, my other term has to be x. Now I'm looking for two numbers that multiply to 10, but when I do my outers and inners, I get 9x. All right. So if I put 5 here and 2 here, that gives me 10 on the outside and 2 on the inside. Oh, that's not going to work. If I put 2 here and 5 here, we get 10 and we get 2. Oh, that doesn't work. Put 2 here and 5 here. Sorry, I just realized I did the same thing twice. My bad. Outers would be 4x. My inners would be 5x. Great. And this is my expression in factored form. Once again, if you want to do factor by grouping, that's totally fine. All right, you've got 4 examples here. I want you now to use what you've learned and convert to standard form for 6 and 7, convert to factored form for 8 and 9. Go ahead and pause the video and try these 4 examples out. All right, hopefully you've finished them. At this point, 6, 7, 8, and 9 are on this video answer key right now. So if you need to pause it, take a look, make sure your answers are written just like mine, okay? For number 8 and 9, if your binomial expressions are in different orders, remember that's okay because of commutative property of multiplication. All right, I hope this video was helpful. Sorry that it was a little lengthy, but thank you for watching this video that went over factored form as well as how to convert between all 3 forms.